The automotive world remains cluttered with misconceptions that persist despite decades of technological advancement and readily available information. These beliefs, passed down through generations of drivers, continue to influence decision-making at gas stations, repair shops, and behind the wheel. Understanding which commonly held beliefs about vehicles are false can save substantial money, prevent unnecessary repairs, and potentially preserve lives. Consider the widespread anxiety surrounding mobile phone usage at fueling stations. This fear has created an entire generation of drivers who frantically power down their devices before approaching gas pumps, convinced that electromagnetic signals might trigger catastrophic explosions. Research institutions have exhaustively tested this scenario, subjecting fuel vapors to every conceivable mobile phone, signal, and frequency. The results consistently demonstrate zero correlation between cellular devices and ignition events at fueling facilities. The actual dangers at gas stations stem from entirely different sources. Static electricity discharge, particularly during dry weather conditions, poses genuine risks when accumulated charge finds a path through fuel vapors. Cigarette smoking obviously introduces open flames near volatile compounds. Even re-entering vehicles during refueling can generate static buildup that discharges when touching the pump handle. Yet mobile phones, despite generating minimal electromagnetic radiation, have never caused a documented fuel station fire. The persistence of warning signs at gas stations contributes to this myth's longevity. These signs exist primarily to minimize distraction during fuel handling rather than prevent explosions. Station operators recognize that distracted customers are more likely to drive away with pump nozzles attached, overfill tanks, or mishandle equipment. The safety concern involves attention, not electromagnetic interference. Another persistent belief involves timing fuel purchases to maximize volume through temperature variation. The theory suggests that gasoline expands and contracts significantly enough that morning purchases yield measurably more fuel for the same price. This reasoning fails on multiple levels. Underground storage tanks maintain remarkably stable temperatures regardless of surface conditions. The thermal mass of Earth surrounding these tanks buffers against daily temperature fluctuations. Additionally, modern dispensing equipment includes temperature compensation mechanisms that adjust metering based on fuel density. Even if temperature variations occurred, the actual expansion coefficient of gasoline remains too small to generate meaningful savings. A temperature swing of 30 degrees Fahrenheit would alter volume by approximately 2%, translating to negligible annual savings even for high-mileage drivers. The time and effort spent coordinating fueling schedules around temperature theories far exceeds any theoretical benefit. Drivers would achieve greater savings by maintaining proper tire pressure or removing unnecessary weight from their vehicles. Premium fuel represents another area where misconceptions cost consumers billions annually. Marketing departments have masterfully positioned high-octane gasoline as superior, cleaner, and more powerful than regular grades. This messaging resonates with drivers who want the best for their vehicles, leading millions to purchase premium fuel for engines designed to run on regular gasoline. The psychology behind this purchasing decision reflects genuine care for vehicles, misdirected through misunderstanding of fuel chemistry. Octane ratings indicate resistance to premature combustion under compression, not fuel quality or cleaning properties. High-performance engines with elevated compression ratios require premium fuel to prevent knocking and maintain optimal timing. Standard engines derive zero benefit from higher octane ratings. The additional cost provides no improvement in performance, fuel economy, or engine cleanliness. Modern fuel injection systems and engine management computers optimize combustion regardless of octane level, provided the minimum requirement is met. The practice of overfilling fuel tanks to squeeze extra miles between stations creates multiple problems while providing minimal benefit. When gasoline rises above the designated full level, it can infiltrate evaporative emission control systems designed to capture vapors rather than liquid fuel. These components, particularly charcoal canisters, become saturated and fail when exposed to liquid gasoline. Replacement costs often exceed $1,000 for parts and labor. Furthermore, overfilling triggers automatic shutoff mechanisms that return excess fuel to storage tanks, while still registering as a sale. Consumers literally pay for gasoline that never enters their vehicles. Environmental damage occurs through increased vapor emissions and potential ground contamination from spills. The marginal increase in range achieved through overfilling cannot justify these risks and costs. Modern vehicles include precise fuel gauge systems and range estimators that eliminate guesswork about refueling needs. Tire management suffers from widespread misunderstanding about proper inflation pressures. Many drivers reference the maximum pressure molded into tire sidewalls, assuming this represents the manufacturer-recommended setting. This value actually indicates the absolute upper limit the tire structure can safely contain, not the optimal pressure for vehicle operation. The confusion stems from the prominent placement of this information compared to actual specifications. Proper inflation specifications appear in owner manuals and on placards typically located inside driver door frames. These pressures balance multiple factors including load capacity, handling characteristics, ride comfort, and tread wear patterns. Operating at maximum sidewall pressure creates numerous problems. The contact patch between tire and road surface becomes smaller, reducing traction especially during wet conditions. Suspension components experience increased stress from reduced tire compliance. Center tread areas wear prematurely, while edges remain unused. Conversely, underinflation generates its own set of issues. Sidewalls flex excessively, generating heat that degrades rubber compounds and can lead to catastrophic failure. Rolling resistance increases substantially, reducing fuel economy by double-digit percentages. Handling becomes vague, and emergency maneuvers become more dangerous. Regular pressure monitoring and adjustment according to manufacturer specifications prevents these problems while maximizing tire life and vehicle safety. Motor oil selection for aging engines prompts many owners to increase viscosity ratings, believing thicker lubricants better protect worn components. This logic stems from decades past when manufacturing tolerances were looser and engines required viscosity changes as clearances increased through wear. Contemporary engines feature precisely machined components with minimal tolerance variation even after extensive use. Computer-controlled manufacturing processes create consistency impossible with older production methods. Using oil viscosity higher than specified creates multiple problems. Cold starts become more difficult as thickened oil resists flow through narrow passages. Oil pumps work harder to maintain pressure, potentially leading to premature failure. Operating temperatures increase due to additional friction from inappropriate viscosity. Fuel consumption rises as engines work against increased internal resistance. The correct approach involves using manufacturer-specified oil grades regardless of mileage, addressing any leaks through proper repairs rather than masking symptoms with thicker lubricants. The evolution of oil change intervals reflects another area where outdated advice persists. The 3,000-mile oil change, once universal wisdom, no longer applies to modern engines using synthetic lubricants. Contemporary oils maintain their protective properties far longer than conventional formulations from previous decades. Engine management systems monitor multiple parameters to determine optimal change intervals based on actual operating conditions rather than arbitrary mileage. Following manufacturer-recommended intervals, which often extend to 7,500 or even 15,000 miles for synthetic oils, provides adequate protection without waste. However, severe service conditions, including extensive idling, trailer towing, or extreme temperatures may require shortened intervals. Time-based changes also matter, as oil degrades through oxidation even without accumulating mileage. Annual changes represent minimum maintenance regardless of distance traveled. Transmission fluid replacement generates controversy among vehicle owners, with some believing that changing old fluid precipitates transmission failure. This myth contains a grain of truth but misrepresents causation. Transmissions that have never received proper maintenance accumulate deposits and wear particles throughout their operating life. When fresh fluid finally gets introduced after excessive intervals, it can dislodge accumulated debris or lack sufficient friction material suspended in old fluid. The solution involves regular fluid changes according to manufacturer schedules. Rather than avoiding maintenance entirely, fresh transmission fluid maintains proper friction characteristics, provides adequate lubrication, and carries away wear particles before they accumulate. Waiting until problems develop before servicing transmissions virtually guarantees expensive repairs. Preventive maintenance extends transmission life significantly, while neglect, followed by panic servicing, often proves ineffective. Engine warm-up requirements have evolved dramatically with fuel injection technology. Yet conflicting advice persists about cold weather operation. Carbureted engines required extended idle periods to achieve proper fuel vaporization and distribution. Modern engines reach operational parameters within seconds thanks to computer-controlled fuel delivery and precise mixture control. The transition from mechanical to electronic fuel management fundamentally changed cold start procedures. However, immediate high-load operation after cold starts causes accelerated, where despite the engine running smoothly, metal components have different thermal expansion rates, and clearances remain suboptimal until operating temperature stabilizes. Oil viscosity remains higher when cold, reducing flow to critical areas. Turbochargers suffer particularly severe damage from immediate high boost pressure before oil circulation stabilizes. The synthetic oils used in many turbocharged engines require proper temperature before providing optimal protection. The optimal approach involves minimal idle time followed by gentle operation until full operating temperature is reached. 30 seconds to 1 minute of idle allows oil pressure to stabilize and initial lubrication to occur. Subsequent driving should avoid high engine speeds and heavy acceleration for several minutes while components reach thermal equilibrium. This balanced approach minimizes wear while avoiding excessive fuel consumption from extended idling. Air conditioning operation myths affect fuel consumption decisions for millions of drivers. The relationship between air conditioning use and fuel economy varies significantly with driving conditions. At low speeds, air conditioning compressor load represents a substantial percentage of engine output, measurably reducing fuel economy. Highway speeds change this dynamic completely. Wind resistance from open windows creates more drag than air conditioning compressor load at speeds above 55 miles per hour. The recirculation feature dramatically improves air conditioning efficiency by cooling already processed air, rather than constantly conditioning hot outside air. This simple adjustment can reduce compressor cycling and improve comfort while minimizing fuel consumption. Modern automatic climate control systems optimize these parameters without driver intervention. But understanding the principles helps manual system operation. Battery selection misconceptions lead some drivers to install the largest available unit, believing bigger automatically means better. Physical size must match mounting locations and hold down hardware to prevent movement that damages connections and cases. Electrical specifications must align with vehicle requirements to prevent damage to sensitive electronics. Modern vehicles include numerous computers and sensors that require stable voltage within narrow ranges, while higher cold cranking amperage ratings can benefit cold climate operation. Excessive capacity provides no advantage in moderate conditions. Reserve capacity, measuring how long a battery can supply minimum voltage, offers more practical benefit than raw size. The key involves selecting batteries that meet or slightly exceed manufacturer specifications, rather than pursuing maximum possible capacity. Group size designations ensure physical compatibility, while specifications match electrical requirements. Hybrid vehicle maintenance costs deter many potential buyers who assume complexity equals expense, while hybrid components like battery packs and electric motors carry higher individual replacement costs. Their longevity often exceeds conventional alternatives. Hybrid batteries routinely last 15 years or 150,000 miles, far exceeding the 3 to 5 year lifespan of conventional batteries. The chemistry and thermal management systems in hybrid batteries enable this extended service life. Regenerative braking reduces mechanical brake wear dramatically, extending pad and rotor life by factors of 2 or 3. Internal combustion components experience less stress due to electric motor assistance and frequent shutdowns. Oil change intervals extend due to reduced engine operation time. When total ownership costs are calculated over vehicle lifetime, hybrids often prove more economical than conventional vehicles despite higher initial purchase prices. Insurance costs and registration fees may be higher, but fuel savings and reduced maintenance often compensate. Fuel additive marketing promises miraculous engine cleaning and performance restoration through simple pour-in solutions. While certain additives can remove deposits and improve fuel system operation, claims of returning engines to new condition vastly overstate capabilities. Quality gasoline already contains detergent packages that prevent deposit formation during normal operation. The chemistry involved in fuel system cleaning requires specific concentrations and contact times difficult to achieve through tank additives. Top-tier gasoline, certified by major automotive manufacturers, includes enhanced additive packages that exceed minimum requirements. The minimal additional cost compared to regular gasoline provides better protection than aftermarket additives. For vehicles with existing deposit problems, professional cleaning services prove more effective than bottled solutions. Prevention through quality fuel selection remains superior to attempting restoration through additives. Direct injection engines particularly benefit from quality fuel as they lack the natural cleaning action of port injection. Safety equipment myths, particularly regarding seatbelt usage, represent the most dangerous misconceptions in automotive culture. Arguments against seatbelt use typically cite rare scenarios involving vehicle fires or water submersion where occupants might become trapped. Statistics demonstrate that fewer than 1% of accidents involve these conditions. The overwhelming majority of crashes benefit from occupant restraint systems that prevent ejection and reduce impact forces. Unrestrained occupants become projectiles during collisions, striking interior surfaces or being ejected through windows. Even at moderate speeds, impact forces exceed human ability to brace or control body position. Airbags, designed to work in conjunction with seatbelts, can cause serious injury to unrestrained occupants who strike them at incorrect angles or distances. The physics of collision dynamics unequivocally support seatbelt usage in virtually all scenarios. Modern seatbelt designs include pretensioners and load limiters that optimize protection while minimizing injury potential. Manual transmission fuel economy advantages have largely disappeared with advancement in automatic transmission technology. Continuously variable transmissions maintain optimal engine speeds for efficiency across all driving conditions. Dual-clutch automatics shift faster than human drivers while maintaining power delivery. Even conventional automatics now feature 8, 9, or 10 ratios that keep engines in efficient operating ranges. The additional gears allow engines to operate closer to peak efficiency points across various speeds. While manual transmissions still offer engagement advantages for driving enthusiasts, fuel economy benefits no longer exist in most applications. Skilled manual transmission drivers might match automatic efficiency, but rarely exceed it. The simplicity and lower cost of manual transmission maintenance remain valid advantages. But fuel savings should not drive selection decisions. Driver satisfaction and control preferences represent more valid reasons for choosing manual transmissions in modern vehicles. Engine idling at traffic signals wastes more fuel than restarting in virtually all modern vehicles. Fuel injection systems require minimal fuel for starting, typically less than 2 milliliters. Idling consumes fuel continuously while producing zero forward progress. 10 seconds of idling uses more fuel than restarting, making shutdown worthwhile even for brief stops. The calculation becomes even more favorable when considering emissions and engine wear from unnecessary idling. Automatic start-stop systems validate this principle by shutting down engines whenever vehicles stop, restarting instantly when drivers release brake pedals. These systems reduce fuel consumption by 5 to 10% in urban driving despite additional starter and battery wear. Manual shutdown at longer signals provides similar benefits without requiring special equipment. Concerns about starter motor wear prove unfounded, as modern starters handle hundreds of thousands of cycles when properly maintained. Vehicle color correlation with traffic citations stems from statistical misinterpretation rather than enforcement bias. High-performance vehicles frequently feature bright colors that attract attention. Drivers who select such vehicles often exhibit aggressive driving behaviors that attract enforcement attention. The correlation between color and citations reflects driver behavior patterns rather than color discrimination by officers. Insurance companies have studied this extensively and found no causation between color and accident rates or citations when controlling for other variables. Speed enforcement technology, including radar and laser systems, cannot distinguish vehicle colors. Automated camera systems similarly ignore color when documenting violations. The perception that certain colors attract more citations becomes self-fulfilling when drivers of those vehicles assume they are already targets and drive accordingly. The actual factors affecting citation probability include speed relative to traffic flow, lane positioning, and vehicle maintenance condition. Paint maintenance myths lead many owners to use inappropriate cleaning products that damage finishes. Household dish detergents effectively remove dirt, but also strip protective wax layers that preserve paint integrity. These aggressive surfactants, designed to cut through food grease, attack the polymers in automotive clear coats and sealants. Prolonged use causes premature oxidation, fading, and clear coat failure. The cumulative damage from repeated improper washing can reduce vehicle value by thousands of dollars. Proper automotive shampoos balance cleaning ability with paint protection preservation. These formulations include lubricants that prevent wash-induced scratching and conditioners that maintain surface protection. Regular waxing or sealing provides ultraviolet protection and contamination resistance that dish soap actively removes. The minimal cost difference between proper and improper products cannot justify the risk to thousands of dollars in paint value. Professional detailers understand that proper washing technique matters as much as product selection. Coolant system myths particularly affect drivers in warm climates who believe antifreeze serves no purpose without freezing risks. The term antifreeze misleadingly suggests winter-only relevance, but this fluid serves multiple critical functions year-round. Coolant raises the boiling point of water, preventing overheating during high-temperature operation. Corrosion inhibitors protect aluminum and iron components from electrochemical degradation. Lubricants maintain water pump seal integrity. The pH buffers prevent acidic conditions that accelerate metal deterioration. Pure water lacks these protective properties and actually accelerates corrosion through oxidation. The false dichotomy of avoiding coolant purchases leads to radiator failures, head gasket leaks, and water pump deterioration that cost thousands to repair. Proper coolant mixture ratios provide protection across temperature extremes while preventing internal damage regardless of climate. Different coolant formulations suit different metallurgy, making proper selection critical for system longevity. Understanding these automotive realities empowers drivers to make informed decisions based on facts rather than folklore. Technology has fundamentally changed vehicle operation and maintenance requirements, rendering many traditional practices obsolete or harmful. The financial implications of believing automotive myths extend beyond direct repair costs to include decreased fuel economy, premature component wear, and reduced resale value that compound over ownership periods. Education and skepticism toward automotive folklore protect both wallets and well-being while ensuring vehicles provide reliable service throughout their intended lifespan.